We've been looking at artificial data. Let's take a look at some real data. Here are monthly average temperature for the lower 48 states of the USA. I chose this data set because these particular data, the noise shows very little autocorrelation. In fact, it's very close to white noise. We're going to treat it like it's white noise, which is not a perfect approximation, but the autocorrelation is low enough that we can pretty safely ignore it, treat it like it's white noise, and apply the methods we've been studying so far. Well, the first thing we might want to do is fit a straight line, see if there's any significant increase. If I do that, I do get an upward line, and when I check the statistics, I find that the p-value is so small, there's no doubt that it is a real increase over time. So the USA has been getting warmer over the last 120 years or so. I can also fit more complex patterns. I could fit a quadratic, which would give me a slightly curved rise, and the quadratic term also turns out to be statistically significant, although not as strongly so as the linear term. I can even try fitting a cubic polynomial, and I will find that the cubic term is very strongly statistically significant. So I've definitely got some long-term pattern going on here. And in fact, I can even plot the long-term pattern itself. And the pattern we see is an early rise, then a very slight decrease for a while, and since around 1980 or so, it's been increasing much more rapidly. By the way, these temperatures for the USA are in degrees Fahrenheit, not degrees Celsius. But we really want to consider our smoothing methods. We can start with simple averages. Here are 5-year averages. The most interesting thing about this is that the last data point is so much hotter than the ones that came before it. It also has a wider uncertainty range to it. That's because the last 5-year span from 2015 to the present is incomplete. It doesn't cover a full 5 years. It doesn't have 60 months in it like the others do. It only has 17 or something like that. We can even actually, since the TIM average program does this for it, we can see that they all have 60 months in the 5-year span, except the last one only has 17. Now we can do the same thing, only this time, instead of slicing up time exactly at 5-year boundaries, where there are multiples of 5 years, let's offset the boundaries by 1.4 years. So now, when we see how many data points are in each slice, we see that the last one has 60 months in it, just like all the others, except now the first one, starting in 1895, only has 17 data points. We also see qualitatively different behavior. The most recent 5-year span is the hottest, but the one just before it is not the second hottest. It's more like the fourth hottest. It's the one 2 time slices ago that is second hottest. There's still this pattern of early rise, slight decrease, and then later rise. But now there's more wiggling going around because by taking 5-year averages, we're using a faster time scale and picking up faster variations. Those variations might be real, but they're probably just noise. We could do a 10-year time span, and we see a very steady rise since 1980. But once again, the final time slice only has 77 months in it because it's not complete. The decade isn't over yet, whereas the previous ones have 120 for 10 years, except the first, which only has 5 years worth of data, 1895 to 1900, for 60 months in the average. Once again, we can offset where the time slicing occurs and arrange that the final time slice has a full 120 data point complement. Then we see that with that arrangement, the last most recent 120 months average temperature is about the same as it was during the previous 120 months, although they're both considerably hotter than the 120-month time periods that came before. Well, we can even go to 20-year time span, and we see pretty much generally the same pattern. And once again, we can offset the time slicing so that the most recent 20-year time span has a full 240 months in it. And when we do that, we see that the most recent 240-month period is hotter by far than the 240-month periods that came before it, when we slice them up that way. But we don't necessarily want to slice them up into discrete slices. We could try a boxcar filter. If we do, and then we look at the filtered values and their uncertainties, we can see there's quite a bit of wiggling around, and there's also a lot of very jittery choppiness on the short time scale. That's something that eventually you get used to with a boxcar filter. Well, we can get rid of some of the choppiness by simply using a longer time span. Let's use a 120-point boxcar filter, which is a 10-year time scale. And now when we look at the smoothed value and its uncertainty, well, we're getting something a little more tractable. It kind of looks like maybe it was level for a while, then rose, then declined, and then rose pretty steadily. There are some signs of ups and downs, but I could plausibly put a straight line from here to there with no wiggling and have it stay within the confidence interval mostly, and mostly is all we expect because of the presence of noise. So this is making it look plausible, like there's a very steady increase from 1980 up to the present, at least in terms of the trend, not the noise. Well, let's go to a 20-year time scale, a 240-point filter, and when we plot the smooth values, we can see it's very plausible that there was perhaps some level, then early rise, then decline, and then since, maybe 1970 or 1980, a very steady rise. There's some wiggling around, but that's plausibly just a manifestation of the noise. Now, the boxcar filter is a good one. It does tend to be kind of choppy, though. A less choppy filter is a tent filter. Here is a 5-year time scale or 60-point tent filter. Enough wiggling around that we probably want to use a longer time scale. Here's a 10-year time scale. Now we see there's definitely a sign of some wiggling recently, but it's still plausible to put a straight line from here all the way up to here and have it stray outside the confidence interval only a little bit and only a few times, which is something certainly plausible as a result of noise. If we go to a 240-point or 20-year time scale tent filter, now we definitely get the look of very steady changes. Level for a brief period, then a steady rise, then a steady slighter decline, and since 1975 or 80, a steady and steep rise in temperature here in the USA lower 48 states. Of course, there are other smooth methods. We could try our Gaussian smooth. When we take a look at it, I've done a Gaussian smooth on a 10-year time scale. The time scale that is used in the program is 2.5 years, but the width of the filter effectively, it's not exactly a correct statement, but it's a pretty good effective statement, is about 4 times that. So it's about a 10-year time scale for the smooth. When I look at it, it's very similar to the 10-year time scale smooth we had with the tent filter. Once again, I can go to a 20-year time scale, actually the scale factor being 5 years, so the effective time scale is 4 times that, or 20 years. And when I plot the smooth values and their error ranges, it looks very much again like the 20-year time scale tent filter. The main difference is that now it extends all the way to the beginning and end of the observed data. Now we can clearly see that it is certainly plausible that it has been rising steadily without any real wiggles other than due to noise since about 1975 or 1980. Incidentally, one thing you can do to help limit the edge effects, the boundary effects you get from a Gaussian filter is, if it looks like there's an overall upward pattern, which it does for these data, one of the ways you can ameliorate that somewhat is fit a straight line. Then fit a Gaussian smooth to the residuals. Then add that straight line fit back to your smooth and plot that. When I do that, it's really not changed very much, although I have gotten rid of a little bit of the apparent downturn because part of the apparent downturn was due to the boundary effect with a Gaussian filter. Well, the Gaussian filter isn't the only thing. I'm going to use a low S filter, but instead of using the built-in version in R, I'm going to use my own low S program. Here it is on a roughly 20-year time scale. It takes a little while to compute because I wrote my own program and it does a lot of calculation, and it's not the fastest program in the world. If I plot the smooth and its error range, I can definitely see very clearly that what it looks like is steady for a while, then a sharp rise, then a slow decline, and then a steep rise since about 1975 or 1980. All our smooths are generally tending to settle on roughly the same pattern. If I compare this from the low S smooth to the Gaussian smooth, I can see it's pretty much the same. Very similar smoothed values and very similar error envelope around it. If I compare them to the boxcar filter, pretty much the same thing. The boxcar filter is quite choppy at short time scales. That's just one of its characteristics. But it's basically showing us the same overall pattern and roughly the same confidence range around that overall pattern. And if I compare it to the tent filter, by golly, same thing again. All our filters are giving roughly the same overall pattern and roughly the same confidence interval, which is a pretty good sign that we're getting a decent handle on things. By the way, there's one more model I'd like to show you for this, and that is this. Let me show you the low S smooth result again. Now I'm going to add onto this the fit I get from a piecewise linear fit to the data. A piecewise linear fit shown by the black line is a set of segments that are all straight lines. In this case, I've insisted that they meet at the endpoints, so we have a continuous piecewise linear function approximation. Notice that the piecewise linear fit, the set of straight lines, it everywhere lies within the error envelope indicated by the low S smooth. That suggests that this piecewise linear fit is definitely a plausible model in terms of what the uncertainties of the data indicate. So there's really no evidence, and in fact we can do more rigorous statistical tests, which we may get into later. There's really no evidence of any difference between the data and steady for a while, sharp rise, slower decline, sharp rise. That's all the pattern that we can demonstrate with absolute confidence in these data. I can add in the other smooths that we computed, and all of them together are not in contradiction to the piecewise linear fit. That does not mean that the data are following a piecewise linear function. It's almost certain that they're not. But it does mean that those are the only changes of slope that we can confirm with confidence. There's one slope here, another one here, another one here, and another one recently. And those are the only changes in slope that we can confirm with statistical confidence in the temperature for the lower 48 states of the USA.